All right, let's take a quick look at a problem from 5.1. 5.1, we were doing compositions of functions. Right? So let's say f of x is 2x over 5 minus x. So that looks familiar. And g of x is 1 over x. Right? So what's our...
I said you're not sharing your
Oh,
screen.
thank you, Cindy. Wake up, Robert. Oh my God, that function is from the test. So f of x, right? 2x over 5 minus x. G of x is 1 over x. Let's do the... What's the domain of f?
Everything except 5.
Nice. So x does not equal 5. Our domain of g is x does not equal 0. But this guy is leading us to the range of g should be y is not equal to 5. Right? The range of g, I don't want y to be 5 because I'm interested in h of x as f composed of g of x. So if I get a 5, if I put some number into g and I get a 5 out of that, when I go plug that into f, it's going to be bad for me, right? So I really want to be thinking of the domain of h, right? Domain of h. Well, g is involved, so I definitely can't put a 0 in there. X is not equal to 0. And what is the x that I put in that I'll get a 5 out of g?
One-fifth.
Yes, so x should not be 1/5 as well. Let's find h of x, which is f composed of g of x. And watch what I do. I'm going to write f, I'm going to write the outside function with empty parens. And what am I putting into those parens? I'm putting in the function g, 1 over x. So I get 2 over x over 5 minus 1 over x. And I have something called a complex fraction. Whenever I have a complex fraction, now and the next few semesters of your mathematical career, you want to clear out those interior fractions. So just like we did when we did difference quotients with rational functions, I'm going to just take my interior LCD over itself and clear out my fractions. So I get h of x is 2 over 5x minus 1. So there's my composition of functions. I always want, if it's a rational function at the end, I always want it as a single-factored numerator, single-factored denominator, right? So I just have, right? So that's what I have here. And it's going to happen in Calc 1 a lot. You're going to have an answer, you're going to think you've done everything right and probably will have. But then when you look at the answer in the book, it looks completely different. It means you got more algebra to do, usually, right? So, let's find something in the domain of g that's not 0 or 1/5. Somebody pick something in the domain of g for me.
Two.
Sure, 2. So let's find g of 2. G of 2 is 1 over 2. Done. Easy, right? So let's now find f of 1/2. Because that's what we're doing. We're putting an input into g, we get the output of g, that goes into the input of f, and then we get the output of f. So f of 1/2 is 2 times 1/2 over 5 minus 1/2. So that's 1 over 9 halves, that's 2/9. Everyone okay there?
I don't understand why x doesn't equal 1/5.
Oh, because if I let x be 1/5, right, g of 1/5, I get 1 over 1/5, that's 5. And then f of 5 is trouble. 2 times 5 is over 5 minus 5. Uh-oh. 10 over 0, right? So you're trying to find the range of g that's bad for the domain of f.
Okay.
So now we're going to go into h, but we're going into h of 2, right? And of course we're going to get out 2/9, right? So 2 over 5 times 2 minus 1, there it is already. 2 over 10 minus 1, 2/9, done. I'm just getting an email. Anybody else get an email about advising day tomorrow for math? Benjamin, you might be the only one who got it. Benjamin, will you check and see if you just got something in your email about advising day?
Yeah, let me check.
Well, that was last class, okay? And I think, that was that Monday. It was a week ago. By the way, next Monday you can start to register for classes if you have 30 or more credits. And the Monday after that, it's open registration, right? So I doubt many of you have locked in already 30 credits. You might have, but then if that's true, you've got early, whatever, advanced status, or so you can register next Monday. Everyone else has to wait for the following Monday. All right, today we're doing section 5.2, and we're talking about inverse functions. And one-to-one functions. So the first thing is we have to talk about this. So by the way, what's an inverse function? It's a machine that undoes something, right? So if you think of, I'm on campus, and I'm a sugar addict, so I go buy a Coke. So I put a dollar bill in and hit the button, I get a soda out, right? And then I realize, oh my God, I got to take the bus. So I need my dollar back, right? So thanks, Ben. So I shake up the soda, and then I put it into the undoing machine, the inverse machine. I put the soda in, and I get my dollar back, and I can get on the bus, right? So I need something to undo things at times, right? Like if I always parked head in spots, I have to be able to put the thing in reverse to get it out, right? With my car. So we need these inverses, and functions that have inverses are pretty powerful. If you think about being able to shoot a rocket into space, you got to think of a way to get home, and it's not the same way, right? So that kind of idea, you have to be able to think about undoing something, right? Especially for what we're doing, the bio or the medicine, or the computer science, the engineering, all of that. We had better be able to get back to where we started, right? So first thing we have to talk about are one-to-one functions. So one-to-one functions are such that if f of A equals f of B, then A equal B. Okay, so So this is a definition of a one-to-one function, and I'm going to tell it to you like a human, okay? But what is f of a? Is that a y value or an x value?
Y.
A y value, right? So I've got what kind of y values in this light blue here? What kind of y values do I have? I got two y values, right? But what are they to each other?
The same.
The same. So if I have equal y values, then I
They're
better.
the same function.
I have. Well, no, it's definitely the same function.
Oh, just okay.
Right, right. No, I like that's good though. If I have equal y values, then I better have
Same X.
the same equal x's or the same x exactly. Okay, so now let me say this is like a human would say it, not a math nerd, right? There are no repeated y values. It's the easiest way. No repeated y values. That's the easiest way to say it. The function never hits the same height twice or more. It only gets to that height once. So it might be a height of 7. It can only have a height of 7 once. It might be a height of negative 11. It can only have that height once. It cannot hit that height again. So the nerd way we've said it in the past that you should recognize is for each unique y, there is one and only one x. Where have we heard that before? Where have we heard that language before?
Beginning of when we started doing functions.
Exactly. This is our definition of functions, but the x's and y's are switched, and that's the super key. Is x's and y's are switched. Domains and ranges are switched. Inputs and outputs switch. So we can say this the same way we were able to understand what a function was, right? We can say a function is one-to-one if the graph passes the horizontal line test.
Professor one-to-one is a way of defining inverse functions.
Once I know a function is one-to-one, then I know I can find the inverse function.
Got it.
Because what has to happen is my function has to be a function. Duh. It's got to be well defined. Every time I hit the button, I get a soda out, right? But now I have to get a function in the reverse way, right? So now so it used to be I have to have for each individual x, I must have a unique y, one and only one y. And now I'm saying for each unique y, I can have one and only one x. The machine's got to work backward and forward. So for example, if I look at f of x is 2x over 5 minus x, right? What's my horizontal asymptote here?
2 over 5.
Mm-mm.
1.
Nope. What's the mother of the upstairs? 2x. What's the mother downstairs? Negative x.
Oh,
The
yeah.
x is canceled.
I was thinking 5 minus x.
Right,
I
right.
took the whole thing.
Yeah. So negative 2 is my horizontal asymptote. What's my vertical asymptote?
1.
Yeah. What's my intercept?
What, x or y?
Yes.
Oh, you want both?
Well, it happens to be that they're both the same.
Oh, okay.
Yeah. Right. When the numerator is 0, I get 0, 0. When x is 0, I get 0, 0. what's the short run at 5?
It behaves like 1 over negative x.
Nice. So negative 1 over x is going to be down on the right and up on the left. And so, and it makes sense because it has to go through 0, 0. I missed it, but you know what I mean. So, 1 to 1, right? Passes the vertical line test. If I draw a vertical line anywhere, it's only going to hit a single height. And that's what I need it to be. I need it to be, right, only hit a single height. How we doing? We understanding? Yes? Okay, good. So I'm going to give you a function. I'm going to ask you to show me that it's I'm going to ask you to show me that it's 1 to 1. Then I'm going to ask you to find the inverse. And then once you find the inverse, there's a way for us to tell that we have a function and its inverse, and that's a composition of functions. We're going to compose the two together, and it should give me my input back, right? So I used to think about that soda machine. I would be putting $1 in the soda machine. I know we don't do this anymore, but you put that $1 in the soda machine, and it keeps spitting the $1 out, right? And you think it was too wrinkled or something, but it wasn't. It just happens that the machine had its inverse inside. So I put the $1 in, it turned it to a soda, it took the soda, turned it back into $1, and it shot the $1 back out to me, right? And so, right, I thought it was too wrinkled, but it wasn't. It was just undoing the whole process and giving me back what I started with. So when I compose functions together that are inverses, I should get back what I started with, which is x. Okay. So I'll put a little bit more detail in that in a second. So if f is 1 to 1, then f inverse exists. And you'll see that I'll write f inverse as g a lot. I don't like writing that f to the -1 power because students think it means -1 power. It doesn't mean reciprocal. It's not even read f to the -1. It's read f inverse, right? So if you see 2 to the -1, it doesn't mean the inverse of 2. It means the reciprocal is 2, and they're different, right? So this is 1 over 2, right? But f inverse does not mean 1 over f. Okay? So just be careful of that. So if the function is 1 to 1, then the inverse exists, which means we can find the inverse. So I've got to teach you how to find an inverse now. So let's start with something nice and simple. Y equals 3x minus 5 is 1 to 1. How do you know?
Wouldn't we have to make it f -1?
Well, yes, I want to, but just looking at this function, right? How do I know that's 1 to 1 right away?
The function's linear, so
Function's linear, right? So it's on an oblique, yes? Right?
Yeah.
Yeah, I only touch this point.
So it only hits every height once, right? Okay, so but we want to show f of a equals f of b implies a equals b. So f of a would be what? 3a minus 5. And what's f of b? That's right, 3b
3b
minus 5. Yep. I'm going to add 5 to both sides and divide by 3. Done. So f is 1 to 1. Right, just a quick side note. Y equals x squared is not 1 to 1, right? Right? You agree?
Yeah, it reaches the same line twice.
Right, so if I draw my horizontal line, it hits twice. And watch what happens there. A squared equals b squared leads to what? Square root of a squared equals plus or minus square root of b squared. So I get a equals plus or minus b. I need it to be a equals b. So this is giving me two different x values, right? An x value of positive b and an x value of negative b. So not 1 to 1. Since f is 1 to 1, I can find the inverse. So what we do is, instead of using f of x, we write, right, so I'll say this is f of x here, sorry. So we say, okay, we have f of x equals 3x minus 5. Replace y equals f of x. So I get y equals 3x minus 5. And now I want to solve for x. Right, so what do I get? Y plus 5 equals 3x. Don't let me go too fast. If I'm going too fast, slow me down. You're paying me for this torture. Please hit me again. And now I'm going to divide by 3. And then I'm going to switch x and y. Switch x and y. So I get y equals x plus 5 over 3. And then rename y equals f inverse. And I say equals g. So f inverse of x is x plus 5 all over 3, which I'm going to call g. Makes it a lot easier. So the thing you have to see is that I've switched my x's and y's. And this is the key to finding this undoing machine. What was my input has to become my output, right? So I had an input, got an output, and I switched them to undo the process, right? So I've got my f of x, 3x minus 5, and I've got my g of x equals x plus 5 over 3. I want to just double check them real quick. Not prove that they're inverses, but just demonstrate that it seems to be an inverse. Someone give me something in the domain of f.
4.
Thank you. So f of 4 is 3 times 4 minus 5. That's 12 minus 5. That's 7. What I want to do now is take that output and put that into g and see what happens. So g of 7 is 7 plus 5 all over 3. That's 12 over 3, and that's 4. So you see my machines undid each other. We don't say opposite, right? We say inverse. Now, the ultimate guide to verifying that you have inverse functions is that you should compose them, right? So here's my little theorem. If f and g are inverse functions, then f composed of g equals g composed of f equals x. I will get back all the way back to my original input. Like the dollar. Dollar in for the soda, soda in for the dollar, I get the dollar back. Inverse machines. Right? So if you can see what's my input here is x. What's my input here is x. So when I compose inverses, I'm going to get x. I'm going to get what I put in. So first let's find f composed of g. What's f?
3x minus 5.
Nice. So 3 open paren minus 5. And inside of that open paren, I'm putting in g, right? X plus 5 over 3. Obviously, the 3's are going to cancel. So I get x plus 5 minus 5. The 5's are going to cancel, so I get x. That's what I wanted. So it looks like it's working that way. And now what's funny is inverse machines, you could have f and f inverse, but g and not g inverse. You could have an inverse one way, but not both ways. It's weird. Like
So you're saying g of x can go back to f of x, but f of x doesn't always go back to
exactly. And
Okay.
so and the perfect example of it is x squared. That has no inverse. And the square root of x, which does have an inverse. Right? How can I undo square rooting? By squaring. How can I undo square rooting? How could I undo square rooting by squaring? How could I undo squaring by square rooting? But that one's weird because when I take a square root of 4, I can get a plus 2 or a minus 2. So there's you know, the example where it acts weird. But let's find g composed of f. So g is parenthesis plus 5 all over 3. And what am I putting in there? The function f, which is 3x minus 5. So clearly the 5's are going to cancel. And then the 3's are going to cancel. And I get what I wanted.
So, Professor,
Yes.
in order to check if g is really the inverse, will we have to plug in f of x into that inverse function?
Exactly. Yeah,
Okay.
you do the two compositions, f with g inside and g with f inside.
Okay.
And
And since you said that f of x doesn't always have to link to g of x, even if that wasn't x, would we still just have to go and check the next one to see if it actually is inverse?
Yeah, if the first one broke, you don't have to go forward, right?
Okay.
Yeah. It will, like the book will usually give you the first one that works, and then the second one won't work.
Got it.
They're just trying to make you work more. If they give you the first one that doesn't work, they know you don't have to do anymore, right? Yeah, so both compositions have to give me x. Right? So, well, here we go. Let's do a problem. Just like your first problem on the next test. This is your first problem on the next test. I'm going to ask you to show a function is 1-to-1.
And the inverse.
Find the inverse. Do a dummy check on the inverse, and then actually do the compositions, right? And then actually do the compositions that I want to verify that you have an inverse. I probably will even ask you to graph it so that you can give me long run behavior, vertical asymptotes, short run behavior, because some of you didn't even, it's like I didn't even ask the question on the test. You're like, let me just cross that one out on the test. He won't notice. Let's see. This one looks good. So is this 1-to-1? Well, let's do a quick graph. So what would you do on your test? You would put it in your calculator, right? But you can clearly see there's a vertical asymptote at -1, right? Horizontal asymptote where?
At 3.
Almost.
1.
At 1.
Negative.
At 1. Again, take the mother of the numerator and mother of the denominator. X over x.
Oh, right.
Right. Give me a point on here. It looks like when x is 0, I get -3, right? So you can already tell me the short run behavior easily. What does it look like?
1 over x.
Nope.
I mean, negative 1 over x.
Yes. right? Because I have 2 points under in. You see the new crosshair I have, the new origin I have, right? In dashed lines, red and blue dashed, right? And so I'm creating that -1 over x on the side where the points are. I know I have to go through those points, right? Cool. So 1-to-1 for sure about a graph, right? Yes? Everybody with me here?
Yes.
Yep. So passes 1-to-1 since it passes the HLT, horizontal line test. We want to do something a little more sophisticated, even though MathXL, listen to me here, MathXL is never going to ask you to do this, but Robert is. Okay? Prove that this is 1-to-1 using f of a equal f of b implies a equals b. Show that a minus 3 over a plus 1 equals b minus 3 over b plus 1 implies a equals b. I'm going to have the same y values with what I think are different x values, but I'm going to end up showing that the x values are the same. Well, I mean, I don't like fractions. It's not that I hate fractions. I feel better when they're not around. Same with police. But so I want to get rid of fractions. How do we do that?
You have to multiply by either a plus 1
Nice.
or b plus 1.
Nice. Cross multiply, right? Now, I don't know what those people are talking about in the other room, but there's 2 different rooms, people talking. Let's break this conversation up. Let's all be together and agree on something, right? Let's stop this association by distributing. Yes? So I get AB minus 3B plus A minus 3. Is that right? Yes. Equals AB minus 3A plus B minus 3. You're with me? No fractions, no parentheses, right? So it looks like my AB's cancel and my 3's cancel. So I have minus 3B plus A equals minus 3A plus B. And I want to get all my apples on one side, all the bananas on the other, right? So it looks like if I move the A's left, I get 4A, and the B's right, I get 4B. So I get A is B. Yes, 1-to-1. Not bad, right? We okay? Nice. All right, so that means the inverse exists. So if the inverse exists, we can find it. So let's find, right? Let's find f inverse. Well, we start with f of x. F of x is x minus 3 all over x plus 1. That means y is the same, right? And now I'm solving for x. Same idea. I don't like fractions. I don't like parentheses in that order. Get rid of the fraction. Well, maybe not even, but so I get what y is times x plus 1 equals x minus 3. I get xy plus y equals x minus 3. I am now trying to I'm trying to isolate x with the least number of negatives. Okay, it's not wrong to do it the other way, it just gets messier. So I'm trying to get all my x's on one side, right, with the least number of negatives. So if I move the y to the right, I'm going to get a negative y minus 3. And then the x to the left, I'm going to get 3 negatives. Negative x, negative y, negative 3. If I do it the other way, I get less. So that's what I'm going to do. I'm going to go y plus 3 equals x minus xy. Notice I moved the xy to the right. It became negative. I moved the negative 3 from the right to the left. It became positive. So I don't add more negative signs. That's what I'm trying to do. Create the least number of negative signs. It's not wrong to do it the other way, but then you have to do a little bit more work later. Okay? So now I can factor out the x here and finally solve for x. And now replace x and y. And there's my inverse, so I'm going to call it F inverse. In fact, I'm going to call it G. You have a problem just like this. First problem, test 3. I guess if I want better grades, maybe I should just give you the test, huh? There are a lot of teachers that just give A's. It's not me. I'll give you an A if you give me an A. You give me an A, I'll give it back to you. How's that? You give me an A, I'll give it back to you.
Once a one.
What's that, Ryan?
Once a one, like what you put in, you get out.
That's right. So I've got my function. I've got my inverse function, at least what I think is my inverse function. Let me try just a quick number in F, get the output, then try the output in G, and then get the put that into G and get the output of that and see if things switched, right? So what do I have? Let's find, where's F again? F is x minus 3 over x plus 1. Give me something in that domain. Somebody.
Six.
What number?
6.
6, yes. Sure, f of 6. That's 6 minus 3 over 6 plus 1. That's 3/7. I like it. Let's find g of 3/7. What should I expect to get if I have an inverse? I should expect 6, right? So I have 3/7 plus 3 over 1 minus 3/7. I'm going to clear my fractions with a 7 over 7. I get 24 over 4, which is 6. Done. It worked. I think I have an inverse. So I want to verify. The only way, I can't verify this way. I can just see that it seems to work, right? I can say, right? I can't do it for every x value in the domain because it will take me forever, right? And I'm already old. So I want to be able to do it in general, and that is with the composition of functions. So I compose these two functions together, and then I should see a result of x in either composition.
So you can't plug in 3 or -1, right? Because then you would get 0.
Yeah. So yes. So exactly. And guess where those pieces are happening? Guess where those pieces are happening?
The asymptotes.
Exactly. There's the place where there's no x or y. Right? There's a piece missing from the domain and a piece missing from the range. And that's all, it's all connected. I just wrote a really bad joke. It's raining the other day and I didn't want to go out, and my girlfriend said, "Put your asymptotes." I'm sorry. I just think the word is funny, so I... Okay, here we go. F composed of G. F is x minus 3 over x plus 1. What am I putting inside? X plus 3 over 1 minus x. On your mark, set, go. I'll give you a minute. but we want to be able to show that work, right? So we take the interior denominators over itself, right? So x plus 3 minus 3 times that 1 minus x, all divided by x plus 3 plus 1 times that 1 minus x. Is everybody okay here? You see what's happening? So I get x plus 3 minus 3 plus 3x over x plus 3 plus 1 minus x. And it looks like my 3's will cancel here, my x's will cancel here. So I get 4x over 4, which is x. Right? Everybody okay there? Nice. G composed of f, right? My function g is x plus 3 over 1 minus x, and inside I'm putting my function x minus 3 over x plus 1. Wait do you see the computer science students in here when you do this stuff with linear algebra? It's so quick, which is why it's so important to us. All of these kind of calculations done for computers have to be quick. Like a computer will fix the wings on a flight in turbulence, right? And it's all linear algebra saying, okay, where should I adjust the wing? And it had better be quick, right? Oops. Nice. Worked. Pretty easy, right? Kind of fun. If it's not fun, make it fun. Go find problems like that in the book. Make sure you do one with a rational expression, because that's what I'm going to ask you in the test, right? I showed you the linear because it's really easy. I showed you the rational because it's not as easy, and that's the kind of level I want you to be able to do, right? Now, let's look at the graphs of these two functions. So it's because the functions are created by switching x's and y's, there's something unique. No problem, Jamal. There's something unique about something on the graph, okay? So let me bring my Desmos up. And let me wrap these two functions. So my first one was what? Remind me, x plus, is it x plus 3? What's the numerator?
X minus 3 and then x plus 1.
Okay. X minus 3 all over x plus 1, right?
Yes.
Thank you. And we had put in the point. What point did we put in? 6? What did we put in? 6?
Yeah.
Yeah. So we got 6 comma, I forget, 1/7? What was it?
3/7.
3/7? Yep, thank you. And let's put our inverse function in. And that one is, help me.
X plus 3 over 1 minus x.
Thank you. X plus 3 all divided by 1 minus x. And you can see there's symmetry here, right? Remember, light blue is the original, purple is the inverse. But more important is when I put in this point of 3/7, comma 6, there's a connection between these 2 points, is that they're reflections of each other, right? It's a reflection of each other over this line, y equals x. Because when y equals x, that's when x is the same as y. When I switch x and y on the line y equals x, I get the line y equals x. So this is the mirror for any function and its inverse. The line y equals x is where x and y are switched already. So it's the mirror for when I'm switching the domain and range of my functions, right? Pretty cool. And if you turn this one right 45 degrees this way, you'll see the cooling towers of the nuclear power plant, or where Homer Simpson works, right? And it's also called a hyperbola. It's in chapter 10. I hope we get to it. So, pretty interesting when you graph a function and its inverse. You're always going to get this reflection, right? Like what was the one we had before, right? Oops. What was the one we had before? 3x minus y equals 3x minus 5, right? And I'll put the line y equals x on there, right? And now watch what happens. It's gonna give me a mirror of that green across the purple, right? And what was our inverse there? X plus 5 all over 3, was that right? And now you can see the green and the green and the black are the reflection, right? What number did we put in for that one? Do you remember? Can you look back on your notes for me? What number did we put in there?
I think it was 2.
Yeah, so we got 2, 1, right? Six minus 5 is 1, right? So 2 comma 1 on the original function, and then 1 comma 2 should show up on the inverse. There it is. So what's interesting is when we switch x and y, right? When we switch x and y, what do we rotate by if we switch x and y? What angle?
Is it 90?
90. So here's my x and y. So you can see my positive x-axis moving this way. Now when I switch x and y, I want things to behave the same, okay? So if I switch my y to here, I want the y to be positive here and the x to be positive here. Okay, but if I rotate by 90 degrees, right, my y is going the wrong direction. So not only do I have to rotate by 90, I have to flip it around. So now I get what's the inverse. So that little reflection about that line y equals x is me, right? Okay, I switched the x and y, but I'm rotating by 90, but I have to flip the paper over too. I have to be looking from the other side of the paper in order to keep things on the right axis. Which is an interesting point when you move to Calc 3, right? So your engineer's going to multivariable calculus. When you start looking at things in the XYZ plane, you have thoughts like that. Right-hand rule. Have you heard of right-hand rule for physics? So you have to make sure things are pointing in the right direction if you're moving things around. You still want to keep things in proper orientation, right? You don't want to all of a sudden be flying upside down in a plane thinking you're right side up. Dangerous. All right, I don't want to do anything else. Friday, let me stop my